In your most recent lab that we did, we were checking solutions and trying to evaluate whether they conduct electricity or not. And so we were trying to differentiate between electrolytes and non-electrolytes. To do that, we used a conductivity tester, at least in my demonstration I did. Here you see the tester with the open circuit, the wires are not connected to each other. You can see the battery that's attached to the circuit, and you can see the LED that will light up if electricity does indeed flow through the circuit. In the lab then, we were trying to evaluate if some of the solutions that you were examining were electrolytes. We know that electrolytes are any solutions that will conduct electricity. In order to do so, though, we know that there are a couple of requirements. The first being that there have to be charges present in the solution that you're examining. But that's not sufficient. You also have to have these charges be mobile. They have to be able to move around as the electricity is flowing through the circuit. An open circuit then, when you put the wires down into your solution, will now be complete, and the light bulb that had not lit up before will now be lit. And in the lab, you didn't have a light bulb, but you had a tester that connected to your lab quest, and you could actually see the amount of electricity being conducted by the circuit. Here in this diagram, you can see why that's happening. You can see the two wires that are dipped down into the solution have a positive or negative charge coming from the battery. The charged particles that are in the solution then will be attracted to the oppositely charged plate. And this motion between the two plates, you can kind of see that with the dash behind each of the charges trying to indicate which way they're flowing. That flow between the two plates then is what causes electricity to flow through the circuit, and you were able to pick up a reading on your lab quest. However, some of the solutions that you looked at were non-electrolytes, and non-electrolytes simply do not conduct electricity. And the reason for that is there aren't any charges present in the solution. And if there are no charges, then when you dip the wires, the electrodes down into the solution, there's nothing to be attracted to the electrodes. The circuit will remain open and no current would have been detected and you would have gotten no reading on your lab quest. Here you can see one of the ones I had tested in class, ethanol. Ethanol is a covalent compound. It does not break into charges, so there's nothing to be attracted to the electrodes, and you can see the light bulb stays out. So there's all sorts of solutions that could be electrolytic that would conduct electricity. Here's several listed. There are ones that I either demonstrated or you tested in the lab. In all situations, the key was charges were present and the charges were mobile. So what was it that was common to all of those electrolytes? Well, they had to produce charges, and this can happen either through dissociation. As you can see here, I have two ionic compounds. We know that when you dissolve an ionic compound, they have to break apart in order to dissolve. So charges result in the solution, and of course they would be attracted to the electrodes and close the circuit. A second way that a solution could be electrolytic is if ionization takes place. On first glance, it looks like it's dissociation, but when you look at my two examples here, the first one with hydrochloric acid, you can see it's actually interacting with the water and a chemical reaction's taking place, and you see as a result charges are produced and they're mobile, and hydrochloric acid would have conducted electricity. You should have found that. The second example there is ammonia. Ammonia is a base, and when it is mixed into water, it also reacts with it. But again, you can see charges are being produced, and ammonia would also have been electrolytic. So you have to have either dissociation or ionization, and it depends on what type of compound that you're dealing with. On the other hand, non-electrolytes, they neither ionize nor do they produce any sort of charge when you put them into solution. They don't dissociate either. So no charges will be present and there's nothing left to be attracted to the different electrodes. So ionization versus non-ionization. So some compounds, they look like they might ionize, but in fact, from an energy point of view, there just isn't any impetus for them to ionize. And so something like the alcohols, they don't conduct electricity, though they have groups that look similar to those found in solutions that do. In your lab specifically then, you had looked at these three ionic compounds and you should have found that they were electrolytic, and you should have noticed that they varied in how much electricity was flowing, and you can see from their structure that there would be some hint as to what caused the variation in the amount of electricity recorded by your lab quest. On the other hand, a second group you had were covalent compounds. They were also electrolytic. They all conduct electricity: hydrochloric acid, acetic acid, and phosphoric acid. And they're not ionic, so they must be ionizing in some manner. Again, we should have seen some variation, so we would want to understand why there was a variation in the amount of electricity. The final group that you examined were covalent compounds that were in fact non-electrolytic. So we know that these are not going to produce charges. They're neither ionizing nor dissociating. There were no charges that were going to be attracted to the electrodes, except with the tap water. You should have seen some kind of measurement, some kind of flow of electricity with the tap water. And we would want to understand, well, what was the difference between tap water and the deionized water that you used?